Hey everybody, this is Mr. Beckstrom, and today we're going to go over section 4.3. It's what the derivative tells us, and we're going to learn a couple of different ways here to find out where the local maximums and local minimums are. In a function, we're going to be using the first derivative test, and we're also going to be using the second derivative test, which is also the test for concavity. The first derivative test is when we we find the critical values. And then we separate those critical values and see if the derivative is positive or negative in those intervals, and then we can see whether the curve is increasing or decreasing, and then at a place where it goes from increasing to decreasing, we're going to have a local maximum, and then at a place that it goes from decreasing to increasing, we're going to have a local minimum. And for the test for concavity, if the second derivative is positive, that means it is concave up. So we have like a bowl sitting on a table. So that means we have a local minimum. If the second derivative is negative, then it's concave down. And that means that it's like a bowl upside down, which means that we're going to have a local maximum. Alright, so let's go ahead and take a look at a function and see how this works. So for this one, I want to go ahead and do the first derivative test. First derivative test to go ahead and locate the local mins and local maxes. So go ahead, see if how far you can get, and then when you're ready, unpause the video and we will go through the solution. Alright, so the first thing that we need to do here is just find the derivative of this function with respect to x. And that's going to give us, this is 1/3 x cubed, so the 3 comes out front, canceling out the 1/3, so we're just going to have an x squared. The 2 comes out front, canceling that 2 there, so that's minus 5x and plus 4. So here is the derivative of the function, which this equation gives us the slope of the tangent line at some value for x. But now we're going to set that this function equal to 0, because we want to know where we have a horizontal tangent line, because a horizontal tangent line indicates a possibility for a local min or a local max, and sometimes not either one. And as a side note, let's take a look how it could possibly be not either one. If I took a look at the function, I'll do this off to the side, just y is equal to x cubed, and we take a look at that, and it goes something like this. It's not going to be perfect, but something like this, right? And we actually do have a horizontal asymptote right at x equals 0 here, but notice that it's increasing, 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 and then we have a slope of 0 right here, and then it's still increasing. So some functions like this, it can continue to increase or continue to decrease after that 0 sloped tangent line there. So make sure that you test it, even if you think, oh, well, this is positive, so then this has to be negative, therefore I have a maximum. Sometimes you don't. Alright, so let's go ahead and finish this one here. Just wanted to kind of show you a case where that would not happen. But we're going to go ahead and factor this and set it equal to 0. So we're going to have x minus 4, and we're also going to have x minus 1 when we factor that. And that gives us the critical values of 1 and 4. So the next thing I'm going to do to use this first derivative test is I'm going to set myself up in a little number line. You can do it however you want. Put the 1 and the 4 here. And I want to find out whether the derivative is positive or negative here, positive or negative here, positive or negative here. Now you've seen with a lot of these what I like to do is just put that function in my calculator and then put some value in the table. We'll do it both ways. So first I'm just going to kind of do this by hand. What are we going to do here? Okay, so let's take a value that's less than 1. The easiest one to test is 0. If I put a 0 in here, I'm just going to get a positive 4. So this is going to be positive here. Now if I take a value between 1 and 4, let's take 2, plug a 2 in the derivative function here. I'm going to have 4 minus 10, which is negative 6, plus 4 is negative 2, so that's negative there. And then if I take a value greater than 4, so let's say 5, I'm going to get 25 minus 25, which is 0, plus 4 is positive. So I'm going from positive to positive, and that tells me that at 1, see I'm going positive and then negative, right? So positive, and then I'm going negative here, and then I'm going positive there. So this tells me that we have a local max at 1 and a local min at 4. Now as promised, let's go put this in our calculator as well. So if I go up here and let's put in x squared minus 5x plus 4, make sure that my table set is on ask and auto, and go to my table here, and I'm going to put in those 3 values I did before. So what was that? 0, 2, and 5. And notice I go from a positive to a negative to a positive. Now let's go ahead and actually graph the main function here. So let's go up here and just to kind of verify what we did. So we have x cubed minus, divided by 3, minus 5x squared, 5x squared, divided by 2, plus 4x. And let's see if we get that on a standard here. And we can. And notice that at 1 we have a local maximum, and at 4 we have a local minimum. Alright, so let's do one more, and in the next one we are going to check or use the test for concavity. Find the second derivative, and then we're going to find out at those critical values. So first we find the first derivative, we find the critical values. This is for the test for concavity. And then we find the second derivative, and we plug those critical values in. And if the critical value is negative, that means it is concave down, which means we have a local maximum, and vice versa. Alright, let's take a look at one final one here. This one here says the f of x is equal to e to the x times x minus 7. And here I want to find the critical values, and then I want to take the second derivative or use the second derivative test to check for concavity, and use those results from concavity to determine whether those critical values are local mins or local maxes or neither. Alright, so let's go ahead and work this one out. Let's see how far you can get, and then when you're ready, just unpause and we will go through the solution. Alright, so the first thing that I would probably do with this one is just leave it in the factored form and go ahead and apply the product rule in order to differentiate it. So this is the first term times the derivative of the second. The derivative of x minus 7 is just 1, plus the second term, x minus 7, times the derivative of the first. The derivative of e to the x is just e to the x. And then I have e to the x plus x minus 7, e to the x. I can, and I probably should put a equal sign there, I can factor that e to the x out, and I'm just going to have a 1 plus x minus 7, and this is becoming e to the x times, what is that, x minus 6, x minus 6. Alright, now if we set that equal to 0, set it equal to 0 and solve for x, that'll tell us where the critical values are. Alright, so First of all, the range of e to the x, and let's take a look at that in the calculator. All right, so if I just set e to the x equal to 0, let's look at e to the x. So second e raised to the x. And let's do a standard zoom on that. And this is the exponential function, and it gets really, really close to the x-axis, but it never touches it, and then it just goes straight up. So it never actually reaches 0. So there's no value for x where e to the x is going to be equal to 0. So we just have to look at the factor x minus 6 is equal to 0. And that's going to leave us with just a critical value of x minus 6. Oops, excuse me. X is equal to 6. X is equal to 6, right? Because we set that equal to 0. Now I want to use the second derivative test in order to determine whether this value at 6 is a maximum, local maximum, or local minimum. So let's take the second derivative of that, of this function here. So I'm going to use the product rule again. So product rule again of x, and that's going to equal to, well, the first term times the derivative of the second term. You see a little pattern here going on, plus the second term, x minus 6, times the derivative of the first term. And then if we factor out a e to the x there, you're going to get e to the x, and then you're going to end up getting 1 plus x minus 6, so that's going to be x minus 5. So this is your function for the second derivative. And let me make that 5 a little bit better here. All right, and x minus 5. So if we take the 6 and we put it in there, let's see what we're going to get. We're going to get, well, e to the 6th is a positive number, and 6 minus 5 is equal to 1, so that's a positive number. So a positive number times a positive number is positive. That means that this is concave up. And if it's concave up, that means we're going to have a local minimum wherever the lowest point is. So that's what that tells us. So if the second derivative is positive at the critical value, then our function is concave up and we have a local minimum, and vice versa. If it's negative, it's concave down and we have a local maximum. And finally, let's just put the whole function in there to see that we actually do have a local, what do we say, a local minimum at x equals 6. So we go back here, let's go over here, and hey, look, my e to the x is already in there. So let's just put times x minus 7, x minus 7. And let's graph that. And it's kind of hard to see it, so let's go way down in our window here. So window, we were at negative 10. Let's go to negative 100. Just really far down, and we'll change the scale to like 10 here. And graph that. Ah, wow, we still can't see that, can we? All right, let's go down even farther here. Let's go down to 1,000 and change that scale to 100. And there we go. Now we can see it. So 1, 2, 3, 4, 5, 6. You see if you go straight down from 6, that's where the minimum value, the local minimum value occurs. And I think from this graph, we could probably make a pretty strong case that that's an absolute minimum as well. All right, guys, I hope this helped. If you have any questions at all, please let me know, and I hope you have a great rest of your week. Thanks.